Assalamualaikum warahmatullahi wabarakatuh. My name is Sharifah Nur Aisyah binti Said Regional, EC19059. Today I will present about the analysis of DFIG grid connected wind turbine performance during grid fault on the impact of reactive current injection. Okay. For the introduction, with the deepening of the concept of sustainable development, wind power as a renewable energy has been rapidly developed. Wind turbine are classified into two types as a fixed speed and variable speed wind turbine. A variable speed wind turbine provides more energy than the fixed speed wind turbine, reduce power fluctuation and improve active power supply. In variable speed wind turbine, commonly permanent magnet synchronous generator, which is PMSG, and double feed induction generator, which is DFIG, are being used. Okay. So for the objective, we as a student required to utilize MATLAB or Simulink model of a DFIG grid connected wind turbine, and then we analyze the performance under different grid fault kinds and level at the constant wind speed with and without reactive current injection. Okay. For the design and modeling of the wind turbine, Figure 1 shows the 9 megawatt wind farm and 6 wind turbines generated 1.5 megawatt. The grid transmission line is connected with a high voltage 3-phase source, which is 120 kilovolt. It is connected with a step-down transformer, and then another step-down transformer connected to the DFIG wind turbine. The wind turbine DFIG is connected to a back-to-back converter which controls power flow between the rotor and grid. The rotor side uses IGBT to convert AC to DC power, while the stator side is connected to the DFIG and transmission line with a grid side converter for reactive and active power exchange. Okay, for the simulation result, this is a steady state condition. And then this is different grid fault types and level without reactive current. Three-phase line-to-line fault at 8 ohm for resistance. Three-phase line-to-line fault at 5 ohm resistance for resistance. And then single line to fault at 8 ohm. And then single line to ground fault at 5 ohm for resistance. Okay, for the simulation result, okay, this is without reactive current. This is a three-phase line-to-line fault at 8 ohm and resistance from what we can observe from part before. During three-phase to line fault at 8 ohm for resistance and three-phase line-to-line at 5 for resistance is that the voltage drop from 1 per unit to 0.4 per unit, and from 1 to 0.25 per unit respectively. This is because during a line-to-line fault in the three-phase power system, the voltage decrease is because by a short circuit between two or more phases. This fault condition result in an abrupt increase in current flow and a significant drop in voltage. The defective phase become electrically connected with a line-to-line fault occurs, resulting in a path with a low impedance. And then the defect impedance is significantly lower than the system nominal operating impedance. Consequently, a substantial fault current travels through the fault phases, and then the reduction happens as a result of the fault current considerable increase, and the voltage division effect is caused across the fault and system impedance depending on the setup, fault location, and fault impedance characteristic. The voltage drop precise magnitude may change. Okay, this is without reactive current, but in single phase line to ground on the 8 ohm. So while during single line to line ground fault at 8 and 5. For resistance, the voltage drop from 1 per unit to 0.7 per unit for both conditions. In contrast to line-to-line fault, a single line-to-ground failure often results in a smaller voltage drop. During a single line-to-ground fault, one phase becomes electrically connected to the earth or ground. This makes a path and low resistance between the phase with the crack and the ground. A line-to-line fault, on the other hand, has a bigger fault impedance. Okay. Okay, this is the impact after reactive current injection for the three-phase line-to-line fault at 8 ohm and at 5 ohm. When injecting the reactive current for three-phase line, voltage rise from 0.4 to 0.5 per unit, and the voltage rise from 0.25 per unit to 0.51 per unit for three-phase line-to-line fault at 5 ohm resistance. And then this is the impact for after reactive current injection for single line to ground fault at 8 ohm and at 5 ohm. While injecting the reactive current for single line at 8 ohm, voltage rise from 0.7 to 0.9, and then for the 5 ohm, voltage rise from 0.7 to 0.9. Same to the 8 ohm, different a few values at the back. And then for the conclusion, reactive current injection reduce voltage fluctuation and improve the system's capacity to maintain a steady power supply to the grid by mitigating voltage trips during three-phase line-to-line fault and single line to ground fault. So that's all from me. Thank you.